Welcome to LegisShift AI. Today, we are closing out our financial spreadsheets and stepping into the dirt to audit a massive transformation, AI in agriculture. We are living through Agriculture 4.0, where the worker transitions from manual labor to an orchestrator of complex computational systems. With the global population tracking toward 9.7 billion by 2050, the Earth will need to require a massive 60% scale-up in food production efficiency. To map out how agricultural workers can survive and scale through this tech evolution, let's run a macro corporate tool, a comprehensive SWOT analysis. Think of AI not as a mechanical replacement for human intuition, but as the ultimate data engine balancing the real-world operational ledger of the Earth. Let's kick off with the strengths, the internal, immediate technological capabilities that farmers are deploying right now to supercharge crop yields. The core strength lies in precision agronomy, using advanced machine learning models to map highly complex, nonlinear relationships in environmental data. Farm managers are leveraging random forest and support vector machines to seamlessly classify soil fertility and instantly optimize crop selection profiles. Meanwhile, convolutional neural networks, or CNNs, process high-resolution satellite imagery to detect subtle plant disease patterns long before human eyes can. For weather patterns, long short-term memory networks process temporal sequences to forecast exact harvest timelines with incredible accuracy. Integrating these multi-source machine learning architectures drives a proven 15% increase in total yield prediction accuracy, crossing a 90% certainty threshold. This introduces agentic automation, physical robotic systems acting with independent field intelligence under the remote oversight of human managers. AI vision is even conquering specialty crops, which historically resisted automation due to delicate fruit skins and heavy leaf canopy occlusion. Beyond crops, precision live farming utilizes biometric identification like facial and vocal recognition to track herd health without stressful physical ear tags. Unified neural network backbones analyze thermal camera signatures to diagnose acute illnesses up to 10 days earlier than traditional manual inspection. But every powerful asset on an industrial ledger comes with native liabilities. Let's pivot to the internal weaknesses stalling widespread adoption. The most blinding internal weakness is the extreme upfront capital cost required to purchase and deploy advanced AI-driven machinery systems. While enterprise-level operations achieve a rapid return on investment, these setups remain financially out of reach for smallholder farming communities. Then there is the rural infrastructure gap. Deep learning models require massive, continuous real-time datasets that modern rural cellular networks simply cannot support. Furthermore, workers face critical interoperability boundaries. Data gathered by different equipment manufacturers is locked away in strict proprietary data silos. Without open operational standards, building a single, cohesive system of record is impossible, which completely fractures complex AI decision support loops. There are also real physical and mechanical bottlenecks. Current agricultural robotics move with a caution that feels incredibly slow compared to human workers. For instance, a robotic strawberry picker takes roughly 20 seconds per berry, while an experienced human field worker harvests a berry in just 5 seconds. This creates immediate operational friction, as traditional farm operators face a steep digital literacy curve to effectively manage these automated assets. As informal agricultural communities note online, an algorithm built for sterile environments quickly breaks down when facing the chaotic physical complexity of nature. Let's look at the horizon. What external opportunities exist for macro growth, workforce resilience, and long-term socioeconomic value? Government frameworks aim to turn field staff into data-informed decision makers across food production, emergency response, and forestry management. Consider the remote grading program, where AI evaluates imagery with human metal accuracy, lowering barriers and processing costs for producers. Internationally, organizations like the United Nations FAO are systematically targeting the triple divide across digital, rural, and gender gaps. The establishment of regional digital agriculture innovation hubs allows local workers and global scientists to co-create custom tech solutions together. The World Bank is scaling up 60 distinct use cases, driving climate-resilient seed research alongside alternative credit scoring models. This offers a direct path to market transparency through predictive pricing and smart contracts, insulating vulnerable workers from severe economic volatility. The safety opportunity is monumental. Automation fundamentally alters the industry's risk profile by handling the most physically demanding labor. Empirical studies across Europe confirm that deploying field robotics correlates directly with measurable, nationwide drops in agricultural accident rates. Automated drone sprayers allow human crews to manage aggressive pest control from a safe distance, ending direct exposure to harsh chemical compounds. This drives a massive leap in total factor productivity, allowing farms to boost output using the exact same or fewer environmental resources. Finally, we must analyze the threats, the external systemic risks that could disrupt communities if this technology is left unchecked. The primary socioeconomic threat is structural labor polarization. As AI scales up high-skill roles, it risks completely displacing the middle-level labor class. Without deliberate community retraining initiatives, automation could trigger severe rural depopulation trends and systemic economic exclusion. Then there is the intense battle over data privacy and digital sovereignty. Modern connected farms generate an absolute goldmine of operational data. Without open data protection ecosystems, large technology providers could lock farmers into predatory, non-transparent data exploitation loops. Physical safety introduces new threats too. The integration of massive autonomous machinery introduces entirely novel human-machine interaction hazards. Tragic workplace accidents have occurred when complex robotic equipment failed to respond to immediate emergency stop protocols during field adjustments. Systemic dependency on unverified algorithms leaves the food supply chain highly vulnerable to unexpected technical black swan failure events. So what is the final audit on the agricultural AI ledger? It is an undeniable paradigm shift toward completely data-driven productivity. The ultimate takeaway is a strict human-in-the-loop requirement. Technology must adapt to augment human judgment, not completely erase it. By aggressively funding STEM programs, national apprenticeship models, and accessible digital literacy tools, we can securely upskill the workforce. Thank you for watching LedgerShift AI. Keep questioning, keep learning, and I'll see you next time.